Welcome to 12th lecture of RF and millimeter wave IC design. And in today's class, we'll be continuing our discussion on noise in RF circuits. So we have looked at noise figure. We introduced what a noise figure is, and also we have seen sensitivity and dynamic range. And then we arrived at the discussion of spurious free dynamic range, and I told that we'll be getting an equation for the spurious free dynamic range SFDR. So that we will do first. Uh, so SFDR, from yesterday's discussion, it is a maximum input power for which IM3 products lie below NFL noise floor level to the minimum input power with minimum SNR requirements. Um so I'm trying to bring in the relations what we have studied so far, and thereby obtaining a relation for SFDR with those. So we know that IIP3 from uh, the an estimate method for IIP3, we saw that IIP3 can be written as the input power level plus delta P by 2. This is one equation what we have, right? And in this equation, if you look at this delta P is actually the output power minus the IM3 power at the output. So I'm just giving that notation here. So delta P can be written as this difference in power is basically output power level minus the power level of the IM3 components at the output. So delta P can be written as P out minus P IM3 out. Now, uh, all right. So now what I will do is, uh, in that case, I can write output power in dBm as, so output power in dBm can be related to the gain directly as in the input power in dBm plus gain of the circuit in dB. So input power plus gain in decibels will give you definitely the output power level. If I write a similar expression for this, even for the IM3 products, P IM3 out, I can roughly relate IM3 output products will be equal to, if I'm referring the IM3 products to the input side. So there is nothing called IM3 at the input side, but if I'm referring back to the input side, I can roughly say that the IM3 power at the input plus gain will be approximately your IM3 power at the output. There will be small difference. We know the exact coefficients we know, but for this, the sake of brevity, I'm just taking those expressions into consideration. Now, if this is the case, if I consider, say, just I'm numbering these expressions as 1, 2, this is 3, and this as 4. Now, if I'm just doing equation 3 minus equation 4, I can write output power in dBm minus IM3 power at the output. Yeah, definitely all power levels are in dBm only. So P out minus P IM3 out can be equated to P in minus P IM3 in. So why I'm doing this here is, we define spurious free dynamic range in terms of, or we define spurious free dynamic range such that the IM3 product should lie below the noise floor level. So that is why we are trying to bring in the IM3 components into this equation. So if I can write roughly P out minus PM3 P IM3 out equals P in minus P IM3 in, and if I am putting this as number 5, and if I substitute 5 in equation number 1, I can write this further as IIP3 can be written as P in input power plus the delta P is actually P out minus PIM3 out, that can be roughly equated to P in minus PIM3 in divided by 2. All right. Or if I further write an expression for input power, because we are interested to know what is the maximum input power such that IN3 products will lie below the noise floor level. So if I write P in from this, it can be equated to 2 IIP3 plus PIM3 in divided by 3. I hope this is clear. So input power can be written as 2 IIP3 plus PIM3 in divided by 3, where PIM3 in is nothing but we are referring the IM3 products at the output back to input directly by connecting with the gain of the circuit. So now from definition, when we talk about spurious free dynamic range, we told that there is some input maximum input power, and that maximum input power is you can provide an input signal to any circuit such that the IN3 product should lie below noise floor level. That is a condition. So what I will do here is I will write it as 2 IIP3 plus in place of PIM3 in, that can be equal to noise floor level. So your IM3 products can touch the noise floor level but not peaking out of that. So I'm just substituting PIM3 in with noise floor level, and I'm replacing in this fashion. So this divided by 3. So this is PIM3 P in max expression. So this I'll make as equation number 6. And now from yesterday's discussion, minimum input signal power can be written as SNR minimum, the minimum SNR requirements plus noise floor level. This is equation number 7. Now what is SFDR? SFDR is basically the difference between these two, P in max minus P in minimum. So that can be written as 2 IIP3 plus NFL divided by 3 minus SNR minimum minus NFL. Right. Now if this, if I am solving it, we can neatly write it as SFDR is equal to 2/3 of IIP3 minus NFL minus SNR minimum. So this is your spurious free dynamic range expression. Is that clear? So this derivation is done from the previous IAP3 expression, and also, so one thing what we have done here is we have referred the IM3 products to the input side in order to define the maximum input signal power. We referred back the IM3 products to the input and equated that to noise floor level. All right. So your SFDR can be written as, yeah, so 2 by 2/3 of um, IAP3 minus NFL minus SNR minimum. Now the noise floor level can be further expanded as, if you remember yesterday we saw that what is noise floor level, or the totally integrated noise of the system, that we have, yeah, the noise floor level or total integrated noise of the system is minus 174 dBm plus noise figure in decibels plus 10 log B. All right. So that is an expression for spurious free dynamic range. So we will come back and we'll solve certain numericals related to this SFDR, noise flow level, and IAP3. Before that, we'll quickly go through even the noise figure part of noise figure, the other another one issue in RF circuit. So let us quickly go to noise figure calculations, because this noise figure calculation is important to estimate noise figure of any circuit. I'm just completing this noise figure calculation. So any doubt in this previous derivation part what I have done? All right. So the question is, what is the purpose of finding SFDR? So Parth, I hope you were there in my previous class, yesterday's class. Yeah. So you have seen that. See, for any circuit, what should be the like what minimum input that signal that system can detect, and what can be the maximum input signal given to the system. So these two things are very important, right? So whenever we work with any system, we should know in what range the system will respond, or we should carefully give input signals such a way that your system also should respond properly. Right. So generally we use a performance metric called dynamic range, but in RF systems we are more interested, or the dynamic range is actually extended to something called as spur free or spurious free dynamic range. So whenever you apply an input signal, I'll come back. So whenever we are applying an input signal, we should be careful enough to careful that the IM3 products should not peak, or IM3 products should not come out of the noise floor level, because noise floor level is above that level, all the signals or the signals have some importance above this noise floor level. So that should be within the noise floor level. That is why we are looking at the spurious free dynamic range, and in that range you can faithfully apply some signal and you can get the response from that particular system. Yes, Naveshri. Yeah. So in this case, what I have done is I have actually referred this IM3. So it should fall below NFL. Yes, not spurious free dynamic range. The IM3 products. Yes, Naveshri, it is maximum. Actually, this IM3 products are only at the output, but we are actually referring back to input, and we are defining the maximum input power which can be applied. Right. So that is the whole idea of referring PIM3 in equal to noise floor level.
Sir, but if you
Yes.
consider PIM3 in as NFL,
Hmm.
and after it gets amplified, it will cross NFL in the output side, right?
Uh,
Like IM3 max shouldn't be NFL. Output max should be NFL, right?
yeah. So basically, there is nothing called as IM3 at the input, right?
Yes, sir.
Um yeah. So the upper, yeah, that is true. So what I'm trying to say is, if your IM3 max is NFL, sorry,
Yes, sir.
yeah, IM3 in is equal to NFL. Um, okay, just let me just go back to that. If I'm substituting this quantity, where is PIM3 in? So your PIM3 out is equal to that quantity plus. Okay, so you are referring that if you substitute that equal to NFL, then your PIM3 out will be definitely above NFL, is what you're telling.
IM3 out will be above NFL.
Oh yeah, that is right.
Yes.
Okay. Yeah. So let me go back to this, because in that case, um, yeah, that is true. That is right, Navish. I'll get back.
Yes, sir.
Yeah. Yeah. But anyway, this expression holds good actually for all practical purposes. But I'll get back how we will interpret this PIM3 in, or how we will write this PIM3 in or PIM3 out, and substitute equate that to NFL. I'll get back. If there are other possible ways to interpret that. Okay. Yeah, I hope Lalit, that's fine, Lalit. Yeah, the question, what, 1 second. So Parth, I think you understood, right, what I was explaining? Yeah. So Naveshri, what Naveshri asked was, this is for others who did not understand what the doubt is. So what I did here is, after writing this expression here, P in is equal to 2IAP3 plus P IM3 in by 3. Then I said, okay, that is P in. Now to write P in max, the input signal maximum, what I did is I have equated the input IM3 products equal to NFL. Now the question raised by Naveshri is this: if I'm equating input IM3 power equal to NFL, definitely at the output side, your IM3 products at the output will be definitely above this noise floor level. So is that right to express in that way? Is a question raised by Naveshri, Lalit? I hope you understood the question. Yeah, yes. So I didn't reply to that because I'm trying to understand how it can be interpreted in a better way. Because since we were deriving an expression for the input power, a PIM3 inverse equated to NFL, I'll get back if I'm getting an alternate way to express this. I'll definitely get back. But um, in any way, this circuit, this equation holds good actually. But won't the reference for NFL change as well? Noise floor level. Oh, you meant at the output side, right? Uh, yes, that is also true. Yeah. So definitely, I'll give a little more clarity on that. Because we are, if you look at the noise floor level, yeah, the terms under noise floor level. Um, 1 second. Yeah, noise floor level. Yeah, bandwidth remains same. The receiver, the minus 174 dBm remains same. But noise figure is the single term. So let me check and get back, because noise figure, there can be small difference in the noise figure. Yes, it is input referred, Pratap. Yes. Yeah, whether the noise figure of the system also will be into consideration, I'll just get back and I'll just refer back and give some explanation. I'm not giving some random statements here. All right. Maybe the discussion on noise figure will definitely give little more clarity on that. Yeah. So from our previous day discussion, we said that noise figure is equal to SNR in by SNR out, or noise figure is the measure of degradation of noise when a signal passes through a particular system. Now, probably we'll just revise certain things what we already know. Say for example, if you have a noisy resistor, say if this resistor is noisy, we can represent this noisy resistance, or we can actually uh, equate this noisy resistor as, or model this noisy resistor as, a noiseless resistor with the value R. So let me write this as noiseless resistor, and the noise component can be considered as a voltage source whose value can be written as Vn square bar. So I'll not go back to the basics of noise, how we express root mean square value and other things. You may kindly refer to AICD noise lectures or noise class notes. So if you want, even I can share those materials, and if further doubts are there, I'll go back to the details of that noise. So any noisy resistor can be equated as a noiseless resistor in series with the voltage. So this is one way to represent a noisy component. So in a similar way, for any RF system, say for example, I'm considering an RF system, an antenna followed by an amplifier here. So this is V in, this is V out. Say this is an amplifier, say low noise amplifier, which is providing a gain of AV, and this LNA is noisy, right? So a resistor was noisy, I represented it as a noiseless resistor and a voltage source. In a similar way, what I can do here is, whenever an RF circuit is there, to do or to perform this noise figure calculation, I can also do the same thing here. One is, so that noisy LNA can be considered as a noiseless LNA block in series with the noise component, which I marked it as Vn square. Right. Similarly, on the for this antenna, so antenna will have definitely have some resistance. So that resistance I am considering as source resistance Rs, and the noise of that resistance is actually considered as the Vn square bar of Rs, the noise of that resistance, right? So antenna is represented as, antenna is having a resistance, and that resistance is a noisy one. So that is represented as a noiseless resistance and the noise voltage source in series. Similarly, this noisy LNA is also represented as a noiseless LNA in series with the voltage source. And now on this side, I'll mark uh, the actual input coming to this LNA V, right? And this is output, and the gain of this LNA is represented as AV. So what I'm going to do now is, for a single stage, considering an amplifier stage attached to a antenna, I'm going to evaluate the noise figure of this circuit block, right? So carefully look at the steps how we are going to estimate the noise figure of this circuit block LNA, an antenna and an LNA in series. All right. Can I get some response from the class? Are you guys following this? What we are going to do is a noise figure calculation. A circuit block which was noisy is represented as a noiseless one in series with a voltage source. Similar to that, an antenna resistance is also marked in the same way. Right. Now, if I now this noiseless LNA looking into this side, you will definitely have an input impedance, and I'm marking that input impedance as Zin. So what should be the impedance and how the impedance should be matched, those things we will deal separately in unit 3. So as of now, I'm just marking it as an input impedance. Now, if that is the case, there is an antenna resistance on this side, the input impedance of LNA on this side. So whatever may be the signal coming on the input side, will that signal undergo some attenuation? Because there is a resistance Rs and there is an input impedance. Yes. So if that is the case, I'll mark the attenuation, or I'll represent the attenuation of any signal coming to the input side as attenuation is marked as alpha, and that factor can be denoted as input impedance divided by input impedance plus the resistance Rs, right? Now, what are we interested? We are interested to find the noise figure of the circuit block. Yes, Rahul. So what I was mentioning here is an input signal is available here, V in. Now there is an antenna resistance here which is connected here in series. And if you look at the input of this LNA definitely will have some input impedance, right? I'm not saying that that is infinity in this case or that is some other value, but we know for sure that impedance should be properly matched. But we are not going to the matching part now. Now, if that is the case, if I'm marking the input impedance as Zin, the input signal which is coming at this side or the input side will definitely undergo some attenuation because of these, because you can clearly see that the impedance here or the resistance are forming a voltage divider. And that attenuation I marked as alpha, which is equal to Zin divided by Zin plus Rs. I hope that is clear, Rahul. Yes. Now, what are we looking at? So we are looking at the noise figure calculation, and for that we should consider this port and this side, right? So why I marked in that way is because we are interested to find the signal to noise ratio at the input of this circuit, SNR in, where to be measured. It is measured here because we are going to analyze how the SNR degrades as signal passes through this system, right? Now the system input is here and the system output should be here. So I will be measuring SNR output here at this point. So I'll mark this is the point where I'm measuring SNR out, and SNR input is measured at the input of the LNA. Right, these are the 2 points what I am going to evaluate SNR in and SNR out. So what are the steps to be followed? I should know what is the input signal power, input noise power. With that, I can write what is SNR in. Similarly, I should know what is output signal power, output noise power. Then I can write SNR out. Now for that, you should also know the voltage gain of the system. Then only you can talk about the signal power at the output. Similarly, noise power at the output. right? So we may take some 5 to 6 steps to arrive at the final noise figure value calculation. So let me start like this. Signal power at the input, signal power at the input can be written as, so if you yeah, so V in is a signal here, but that signal is not exactly available here. That signal is attenuated by the attenuation factor of alpha. So if I'm expressing it as power, V in, since it is power, I am writing it as V in square, and the attenuation factor is alpha square. Right, I'm not referring to the resistances, the power with respect to the resistances, assuming that input and output impedances remains same. So signal power at the input is just power at the input is expressed as V in square into alpha square. Yeah, now maybe you'll be wondering why I did this. Alpha square is just to adjust the dimensions, right? So V in square should be multiplied by alpha square. Now similarly, if I write noise power at the input, at the input side, you can see the noise voltage or the noise noise voltage is this one, Vn Rs square. So I will write the noise at the input as Vin, sorry, not Vin, it is the noise voltage of Rs square multiplied by this alpha square again, because that even that noise is also getting attenuated through the resistive network over there. Right. So these are the components at the input side. So if I write signal to noise ratio at the input SNR in, it is just the ratio of signal power to the noise power, which is equal to alpha square V in square divided by alpha square into VNRS square. So this can be further written as V in square divided by VNRS square, square bar. That is SNR in. I hope this is clear. Just for reference, I am just marking it. This is SNR input. Now moving on, if I want to write SNR output, to find SNR at the output, I should know what is the output signal power, what is output noise power. So what is output signal power? So signal power at the output is equal to, that can be equated to, so signal power at the input is this value. I hope you can see this. Signal power at the input is this. This is the signal power at input, which is Vn square alpha square. Now at the output, this signal power will be just multiplied by the gain of the circuit, right? So I'm just writing it directly as Vn square alpha square into, it should be multiplied by gain, but since it is power, I'm just multiplying by gain square, AV square. That is output signal power. Similarly, if I write output noise power, output noise power, it can be equated as, uh, so we have already marked the noise of LNA as Vn square, and that is shown at the output side. So that can be written first, Vn square bar. This should be this Vn square bar term should be understood as the noise of the LNA. Now to this, I should add one more component at the output. What is the other component at the output? We know that noise terms can be added since they are so one is available at the output directly and other term is from the input. Now even the same, the noise power is also attenuated by this alpha term and amplified by the voltage gain term. So I can directly write it as Vn Rs square bar into alpha square into Av square, right? So we can see two terms here in the output noise components. One is output noise of LNA itself, output noise of LNA, output noise of LNA, which is marked as Vn square bar. The second term is the noise of antenna, which is already marked as Vn Rs square into alpha square, which is multiplied by the LNA gain. Multiplied by LNA gain, so that is the second component Vn Rs square into alpha square into Av square. I hope this is clear. If that is the case, I can directly write SNR out. SNR out is equal to the numerator is the output signal power, which is alpha square into Vn square into Av square divided by output noise power. There are two components, Vn square bar plus alpha square into Vn Rs square bar into Av square, right? So this also just marking for the reference. Now to find noise figure, what I can do is I can directly write noise figure can be expressed as SNR in by SNR out. So if I substitute the equations over here, it is first I'll write SNR in, which is Vn square divided by Vn Rs square bar divided by SNR out. So I'll be just taking the reciprocal here. Is Vn square plus alpha square Av square into Vn Rs square divided by alpha square Vn square into Av square. So this is the ratio. Now here you can cancel the common terms. This Vn square and this Vn square can be cancelled. So this can be further written as 1 by Vn Rs square into Vn square bar plus alpha square Av square into Vn Rs square bar divided by alpha square into Ab square. All right. Now again, just for simplification, we can just use alpha into Av as some factor A naught and just simplify that. Or so this could be further written as okay. So what is this Vn Rs square Vn Rs square bar? How can we write this Vn Rs square bar? That is a noise resistance. The noise power of the antenna resistance. So how will we write that? Any answers for that? Do you remember how did we express the noise voltage of a resistance with value R? Is noise voltage is nothing but the power spectral density what we have written. So I hope you remember it as 4 kT into Rs, or for any resistance R it is 4 kT into R, 4 kT into R. Any answers for that? Oh, Pratap, it's not 3 kVt, it is 4 kT into R. The voltage noise spectral density. Yeah, no problem. Yeah, so so this can be further written as, so if I write it as 1 by 4 kT Rs, and if I'm taking that is the common term Vn Rs square, because even in the numerator you can see that, so I'll just write it as Vn square bar by alpha square Av square, just separating, plus just separating the numerator. So it is Vn square by alpha square Av square plus the other term is just 4 kT Rs. Or now if I simplify this further, I can write as 1 plus Vn square bar divided by 4 KTRS into alpha square AV square. This is also one way to express noise figure. So this is noise figure. We express in different ways. Right. So one more thing here. If you look at this expression where you have written 1 by 4 n r square. So if you look at this numerator factor, this numerator factor can be further written as, this can also be written as 1 by Vn Rs square bar into, this is the total output noise factor, right? Because Vn square plus alpha square AV square into Vn Rs square is the, this part is the noise available in the output from the input plus the output noise of the LNA. So altogether I can express it as Vn out square bar divided by alpha square AV square. This is another way to express it, right? So this is how we calculate the noise figure for any circuit block. So we have taken the example of an amplifier here. So just to summarize, mm, noise figure is a ratio of SNR in to SNR out. Uh, we have two components here. One is a circuit and a circuit block of noise, LNA, which is noisy. That is expressed as a noisy LNA and a series voltage source uh, to elaborate or to consider the noise of the LNA. Similarly, antenna resistance is there, and the noise of the antenna is expressed as a voltage source in series to that. Then we have defined the attenuation factor, what the signal at the input will be undergoing, and with that we continued by writing the signal to noise ratio at the input, signal to noise ratio at the output by defining signal power and noise power at both input and output. And finally, we obtained the expression and we have written in different forms. Right. So that's all about how to calculate noise figure. Now we'll be continuing with some numericals related to certain circuits, how to estimate noise figure of some circuits. Right. So that we'll be continuing in the next class. Along with that, after that we will also see because how we have understood the performance metrics for a single stage and later we extended to cascaded stages. Similarly, we'll also calculate how to express noise figure for cascaded stages. Right. So with those topics, we'll be winding up unit 1, but definitely it will take another 3 to 4 classes. Right. So thank you so much for joining for today's class. If you have doubts, we can clarify now. Thank you.